In this video, we're going to look at testing the significance of correlation coefficient, prediction, and outliers. So when we are talking about the correlation coefficient, which is R, this tells us how strong and the direction the linear relationship is between two variables, x and y. Now, it also depends on the data points. How many data points do we have in the sample? And both the correlation coefficients R and the sample size n need to be considered together. So when we talk about the significance of the correlation coefficient, we're going to be doing a hypothesis test. And what we're going to do is determine if the linear relationship observed in the sample data is strong enough to represent the relationship in the entire population. While the correlation coefficient R is computed for the sample data, if the data for the entire population were available, which is unlikely, the population correlation coefficient would be rho. And then we could directly calculate this relationship. However, as we only have a sample data, R will serve as an estimate for the unknown population coefficient rho. So when we do our hypothesis test, we will be using rho, and rho is this funky looking P. So when we do a hypothesis test, it is always in reference to the population. So this is the notation that we will use. Now, sometimes you might see this as a beta, which is, the B beta. So when you are looking at some of the videos, you might find they're going to use beta instead of rho, and that's okay. It's still talking about the population parameter. The hypothesis test that we are going to do enables us to evaluate whether or not the population correlation coefficient is close to zero or significantly different than zero. So we're going to say, is it zero or not zero, pretty much. This determination relies on both the sample correlation coefficient R and the sample size. There are some assumptions that we have to make when we are doing a linear regression hypothesis test. First of all, it has to be linear. There has to be a linear relationship that models the average value of y for different values of x. And they have to be independent. So the residuals are assumed to be independent. Normal. The y values are normally distributed for any value of x. We have equal variance. The standard deviation of the y values are equal to each of the x values. We have to have random. The data is going to be a well-designed sample. That is going to be random sample or a randomized experiment. And we have to have homogeneity, which is similarity of variance and no influential data points. So as before, we are going to talk about the standard deviation. The standard deviation is called the error or residual. And it's not an error as in like we made a mistake. It's the difference between, in this case, what we observed and then this y naught. And this is the error naught. Now, y naught is the predicted. So when you're using your linear regression line or line of best fit, this is going to be what was predicted by that line of best fit or the linear regression line. The absolute value of the residuals measures the vertical distance between the actual value of y and the estimated value y or the predicted value of y using the line of best fit. In other words, it measures the vertical distance between the actual and the predicted. So visually, this is what's happening. So here is the predicted value for y, and here's the actual value of y, and the distance between them is that error. If the observed data point lies above the line, the residual is considered positive, and the line underestimates the actual value of y. If the observed data point is below the line, the residual is negative, and the line overestimates the actual value for y. Each data point not on the line will have a residual, and the absolute value of this error is a distance from the data point to the line of best fit. If we sum up all of those errors, we're going to have something called the sum of square errors, SSE. The standard deviation needs to have this SSE to do the standard deviation. The standard deviation S for the sample is going to be the square root of SSE divided by n minus 2. Well, n is the number of data pieces where I have an x and a y. So n is not x and y. N is the ordered pairs, x, y. So for each ordered pair, n. The sum of squares error sometimes is referred to as a residual sum of squares. So in our book, we use SSE. Some other books and some other sources will use RSS, and that's the absolute amount of explained variation, where R squared, and we've talked about this before, is the absolute amount of variation as a proportion of the total variation. So when you compare the standard deviation of residuals to the y values given of the data to determine if there are any outliers, the smaller the number, the more certain you can be about your regressive model. We will use in our spreadsheets, and if you want to use your calculator, that's fine. You're going to open up the textbook and it's going to show you how to use it with the textbook with your TI 84, 85, 83, or 84. We're going to use this. This is linest, line, I like to think of the line ST, in Excel. You're going to first put in the independent variable, you're first going to put in the dependent variable, and then you're going to grab the column that has the independent variables, and then you're going to put true, true in Excel. But this is going to produce way more information in Excel than we really want. So the highlighted blue is the parts that we're going to pay attention to. This number is the slope. This number is the y part of the y-intercept. This is a standard error of the slope. This is the standard error of the intercept, which we're not going to use in this class. This is the coefficient of determination, which is r. Now you think, well, if I've got this, I don't need to find r, right? Well, yeah, you can take this and square root it, but it won't give you whether or not it's going to be negative or positive, because you're going to take the square root, it should be positive. So you're still going to have to use a correlation in Excel to determine if it's negative or positive, or even do a graph of the data to see whether or not it's going uphill or downhill. This number right here is a standard error or standard deviation. It's called the standard deviation. Sometimes it's referred to as the standard error. This already calculates your degrees of freedom, and this is the sum of squares error. So it's already there for you. So if you take this and you divide by your degrees of freedom, so this is already, by the way, the number minus 2. So if you take this number, which is 197.2907, you divide it by 10 and take the square root of it, you're going to get this number right here. We're going to be using all of these things in blue. They're going to give us more than we need. This is an F statistic, which we're going to talk about in chapter 13. And this is the regression sum of squares. Again, something we are not going to be using in this class. So when we talk about outliers, there are two types of outliers. There's just an outlier, which doesn't really influence the data. And then there's an outlier that actually influences the data. So the influential outliers will have large errors. So that distance between the predicted and the actual, they'll have large errors. With the error is the residual. And we are only going to consider any point that is more than 2 standard deviations from the linear regression line to be an outlier. So to calculate the influential outliers, we will find the y hat, the predicted, minus y, and it's going to be equal to deviation for each data point. Any data point that has more than 2 standard deviations, 2s will be the ones that we consider as outliers. So here is an outlier, but it's not influential because you can see it's almost right on the line. So yes, it is way over here, but it's not going to be an outlier that we concern ourselves with because it's not influencing this line. Now, if you notice that these data points and these data points and these data points are all the same with the exception of this outlier. Now, if I move this outlier down here, you can see the line has moved down. So this is an outlier and it's influential. Same thing over here. This same data points, I move this dot up here, and you can see that I'm going to be more than 2 standard deviations from the line directly up above, not sideways, but directly from the line straight up vertically or vertically down. You can see that those two are outliers and influential. So we're going to be worried about influential outliers. when we perform our hypothesis test, we're going to be doing the test of significance of correlation coefficient to decide whether or not there is a linear relationship in the sample data, and if it's strong enough to use to model the relationship of the population. So what we use, again, because we're using the parameter, we're going to use rho. So HO, the null hypothesis, so will always be, we're using rho, is going to be equal to 0, always. So that's kind of nice. And our alternative, or HA, will be rho is not equal to 0. Rho, again, is the population correlation coefficient. It's our parameter. That means we are always automatically a two-tailed test. So what we're going to do is we're going to draw a conclusion. We can do it one of two ways. We can use the p-value, or we can use critical values. If the test concludes that the correlation coefficient is significant, and it's different from 0, then we say the correlation coefficient is significant. We'd say something, there is sufficient evidence to conclude that there is a significant linear relationship between x and y because a correlation coefficient is significantly different from 0. If we decide that it is not significant, so in other words, it's close to 0, we'd say there is insufficient evidence to conclude that there is a significant linear relationship between x and y because the correlation coefficient is not significantly different from 0. Again, I'm using Excel, but you can use your calculator. All of the stuff is in the book if you're using your calculator. So we are going to find our test statistic. Our test statistic is our correlation coefficient for the sample multiplied by the square root of the degrees of freedom and then 1 minus my r squared. We are going to use in Excel, we're going to do a 2.dis.total, and we will find a p-value with the degrees of freedom as the number of data piece pairs minus 2. The test statistic has the same sign as a correlation coefficient. Note, if r is significant, this means that our r value is between 0.7, the absolute value of r, and 0.9. That's considered significant. If we have values between 0.5 and 0.7, these are moderately significant. And we're talking about the absolute value so that we don't have to worry about positive and negative. And the scatter plot shows a linear trend. The line can be used to predict the values of y for values of x that are within the domain of the observed x values. If r is not significant, or the scatter plot does not show a linear trend line, the line should not be used for prediction. If r is significant and the scatter plot shows a linear trend, the line may not be appropriate or reliable for predictions outside the domain of what is given us for values of x. If you cannot estimate the regression line, your estimate is the average of all the y values. Okay, so here is a table. It shows the poverty rate and cellular usage per capita. It is believed there's a strong relationship between poverty rates and cellular usage. Man, I can't seem to say that today. This is from the years of 2000 to 2019. This is the percentage of Americans living below the poverty line. And this is the cellular usage per capita. So the first thing is, what is the null and the alternative hypothesis? My HO, as we know by default, HO will be rho is equal to 0, and our HA is going to be rho is not equal to 0. So I'm going to leave it up to you to graph the percent of Americans doing a scatter plot, living at or below the poverty line versus cellular usage, and you're going to put that right there. I'm going to also perform the linear regression. Now, I can do that with my scatter plot in Excel, or if you remember, I can use that linest, and I can pull out the information that I need. And it's also telling me to round to the nearest whole number. So I got, for my linear regression line, I got y hat is equal to negative, rounded to the nearest whole number, 2,317 plus 104x. Now remember, when we are doing statistics, we like to have our y part of the y-intercept first, and then of course our slope multiplied by our variable, our independent variable. My correlation coefficient, R, was equal to 0.50477. And is it significant? Well, based on what I said earlier, it's mildly significant. So should the linear regression line used to be modeled to any of the pieces of data outside of the domain, this domain where I've got this percentages, right? So from about 23 to about 25. And based on this being mild in my scatter plot, may not be the best choice to use it outside of the domain. I'm going to find my standard deviation, and that, of course, I'm going to use my ln-est, which is lovely. So my standard deviation I found was 70.4348. Were there any outliers? And the answer was no. The test statistic, my t-score, is equal to 2.48078. My p-value is equal to 0.02322. And based on a 5% significance, based on a 5% significance, in other words, I'm looking at this, my alpha as being 5%. Here's my p-value. There is sufficient evidence to conclude that there is a significant linear relationship between the percent of Americans living at or below the poverty line and cellular usage per capita, because a correlation coefficient is significantly different from 0 for the population. So this is my spreadsheet. I like to label all the things that I'm going to be doing. Oh, you probably want to pause it right there if you want to. You don't have to. And this is my data. So you can see here's my data. Every time I put in anything in green, that means that's the input. And then I put my y hat here, where y hat is equal to my y part of my y-intercept plus my slope times x. So these are my predicted values. These are my predicted values. Now, this is going to be my y hat minus y. So this is predicted, and this is the actual, and this is the error. So I have my error messages. Now, then what I do is I take the absolute value of my y hat minus y, so the absolute value of this number, and I divide it by 2 of my standard deviations. If any of these numbers here are bigger than 1, then I know that that's going to be an outlier. And not only is it going to be an outlier, it's going to be a significant value that is going to change my line of best fit, or my regression line. Also, what I have is my dependent values. So this is my ln-est. I put this in. This is what came out. I have this to the side so I remember what each piece is. So this is my slope. This is the y part of the y-intercept. This is my r squared, standard deviation, degrees of freedom, and residual sum of squares, which I don't need. Here's where I got my r. I use in my spreadsheet, I use the Corel. I did my independent first, then my dependent. ln-est wants the y values, then the x's. Corel wants the x values and the y values. Meh. So here's my t alpha score over 2. Now, this number right here is my critical value, right? So this is my critical value. This is my t-score. Now my t-score is just slightly left of this number, or right, I guess, on the right-hand side. This is slightly to the right of my critical value, which means I made the right decision, but it's just so slight. So I'm making the right decision, but it's not like strong. Here's my alpha, here's my p-value, and I am going to reject because my p-value is less than alpha. And that's it for this video.